So let's start. Good morning, good afternoon, everyone. My name is Frédéric Sauvage, and I'm very pleased with the co-organizers to introduce this webinar. So welcome to all participants to this webinar, which is co-organized by two European projects that are Impressive and TECH4WIN. So we'll take a couple of minutes to present their content afterwards. The aim of this webinar is to provide a state-of-the-art discussion related to the research on transparent photovoltaics from both academia and industry's point of view. And for this webinar, we have the chance to welcome warmly three invited speakers. Professor Xiao Ying Ao from the University of New South Wales, Australia. Professor Richard Lund from Michigan State University in the US. And Professor Aldo Di Carlo from University of Tor Vergata in Italy. We have also the chance to welcome two companies that will be presenting at the end of the workshop that are Armor in France and Ubiquitous in the US. So 250 participants worldwide have been registered, and from many countries I've seen India, US, Canada, Saudi Arabia, Estonia, Mexico, Taiwan, Pakistan, Morocco, Egypt, and most of the European countries are there. This is not only a great success, but it also demonstrates the public interest for still an exotic but a rising topic, that is the transparent photovoltaics. The success of the webinar will lie also through two important things. The first thing, the participation of everyone. Please feel free to ask questions to our speaker within the chat or end left. The second important thing is please mute your microphone to avoid background noise, especially during the questions and during the presentations. So very important, please mute your microphone. So this said, let's make this event alive and also with your success. I hope that you will enjoy the content of this workshop. I will give now the floor to Mrs. Maider Machado, who is representing the European Commission in Brussels, and who is also acting as a project officer for a welcome word. So, Maider.
Good morning, everyone, and welcome to this workshop on transparent PV research and applications. My name is Maider Machado. I work as project officer for the European Climate, Infrastructure and Environment Executive Agency of the European Commission. It's an honor for me to introduce this workshop, which has been organized by the Horizon 2020 funded projects Impressive and TECH4WIN. These projects, together with several other international initiatives, as the ones present here today, are working on delivering transparent and high efficiency tandem cells and modules for building integration applications. Building integrated PV is still a niche market, but if we are able to provide transparent electricity producing construction products, this can definitely play a role in bringing together the PV and the construction sectors, supporting distributed electricity generation worldwide. The applications of this kind of technology do not end here, as we can also envisage, for example, low power devices or vehicle integration applications as well. And the objective of developing an efficient and stable PV cell, which does not absorb in the visible range, and developing a commercial product that can be accepted and implemented by the construction sector is really challenging. But I am convinced that we need this kind of breakthrough research with highly ambitious targets, which are, of course, fully aligned with the European Green Deal targets and the Commission's strategy towards the energy transition. So I don't want to take more time from you. We have very distinguished speakers today with us and very interesting presentations ahead. So I would like to thank the organizers, to thank all of you for your attendance, and I wish you a very interesting event. Thank you.
Thank you, Maida. So we will start with Alejandro Perez Rodriguez, who is coordinator from TECH4WIN. We'll take a couple of minutes to introduce you what are those two projects. So Alejandro, floor is to you.
Okay, thank you very much. So I'm Alejandro Pérez Rodríguez. I'm leading the PV group, the photovoltaics group of the Catalonia Institute for Energy Research, IREC, and I'm coordinator of the TECH4WIN project, which is Disruptive Sustainable Technologies for Next Generation PV Windows. So I'm going to make a very brief presentation of which is the concept of this project, the objectives, and which are the people involved and the groups involved in the project. Essentially related to the concept, we are proposing and working in an innovative transparent PV window that is based on a tandem-like structure, which implies a combination of an inorganic ultraviolet selective multifunctional coating that includes the UV filter functionality with an UV selective solar cell functionality that is deposited in the upper part of the window, and an organic infrared selective solar cell, and this is implemented on the second glass of the window, integrating also an internal distributed Bragg reflector to increase the efficiency of the infrared device. So this would be somehow the schematics of the window structure, including both devices. The motivation is to exploit the IR efficiency potential of organic-based solutions with the robustness and stability of the inorganic thin film solutions, combining sustainable and industrial-compatible technologies with demonstrated potential for cost reduction. So one of the pillars, one of the aims of the technology developments that we are working on in TECH4WIN is this related to the sustainability and to the industrial compatibility. So we need for solutions that can be transferred afterwards to industrial production stages. And the novelty of our approach lies on the capacity of this tandem-inspired structure to protect the most active PV layer, which is the infrared selective organic cell, through the filtering of the ultraviolet radiation by the UV multifunctional coating, extending the lifetime of the device from 10 years, that is the target identified at the end of the project, until 25 years, which is a target identified as a long-term goal. So the main objective is we are working developing a set of transparent PV window prototypes with different size formats, small to medium size format, with strong improvements in the level of transparency and visible quality in the visible region, energy generation, advanced filtering capacities, thermal behavior and energy impact that will be exhaustively tested in a relevant environment for demonstrating their feasibility as a smart window. Here we are summarizing which are the targets, the quantitative objectives identified or defined in the project. We have defined two levels of targets. There are the targets identified at the end of the project, and we have also identified long-term targets after a post-project stage that will be required in order to ensure the transfer of these developments towards industrial production. So focusing in the targets defined at the end of the project, these include photoconversion efficiency of 10 or higher than 10% at cell level, an average visible transmission higher than 60% for the window prototypes, projected lifetime higher than 10 years, and color rendering index higher than 70 in order to ensure a high optical quality window, allowing an unhampered transmission of the visible light through the window, which is one of the main issues. And of course, this is also related to the neutral color character of the devices. So here you have a very short overview of which is the work plan structure. We are structured in 8 work packages, and technical ones and main ones are related to, there's an initial work package 1 about the definition or devoted to the definition and of the requirements or review of the requirements, specification and standards that are related to the window, that are needed for the window to be acceptable in buildings. And these are compromising, of course, the conditioning or imposing conditions about the device design. Then we have the technological core of the project that is structured in 3 work packages. One work package 2 is working in the development of the infrared selective devices, and work package 3 is working in development of the multifunctional UV coatings. And these 2 work packages are working in close correlation with work package 4, which is related to the multifunctional modeling of the devices and window solutions. This includes the modeling and simulation of the optical behavior and electro-optical behavior of the devices integrated implemented in the window for optimization of the device design, and also the modeling of the passive energy properties of the window for analyzing the impact of the window on the weather conditions of the building. All this is feeding, at this moment, the solutions or the developments in this work package are being transferred to work package 5, which deals with the implementation and demonstration of the window prototype, of the first medium-sized window prototype. And then we have also a strong activity related to the analysis of in industrial scalability, to the design of the transfer of all these processes from the lab scale to the industry, including also, of course, the circular economy considerations. And of course, always the transversal work package related to exploitation, dissemination, and project management. So very briefly, just to finish who we are, we have, there is a strong emphasis in this industrial transferability of the processes. The consortium includes a well-balanced structure, including both research centers with strong activity in development of these technologies, and also research groups from companies, from industries. So IREC, we are acting from IREC as project coordinators, and we are dealing with the development of mainly with the development of the UV multifunctional coatings and with the modeling of the passive properties of the window solutions. Onyx Solar is a BIPV company that is acting as industrial coordinator. They are the exploitation and innovation manager, and they're in charge of the prototyping and demonstration for the implementation and assessment of the PV window prototypes. CEA, on the French Research Institute, are working in the infrared selective organic devices and in the optical modeling for optimized device architectures and LCE analysis. IMEC, the Research Center, collaborates with IREC in the development of UV multifunctional coatings using alternative technologies. We're working either using oxide or chalcogenide-based strategies, and also the upscaling of the sputtering processes for the medium-sized devices. Techniker, the Research Technological Center, Techniker works in the development and implementation of the infrared internal drag reflector for the enhancement of the efficiency of the infrared selective devices. Armor is the company that is working in the transfer of the OPV processes from the cell level, from the lab level, that is developed at CA to roll industrial process conditions, and also is in charge of the upscaling of the processes for the development of the medium-sized models for the medium-sized window prototypes. Advent is a chemical company which deals with the design and synthesis of new high conjugated polymers for the optimized infrared selective devices. And finally, we have Kenosystic, which is an equipment company which is in charge of the industrial techno-economic assessment related essentially to the sputtering processes that are industrial compatible processes that are used for the definition of the and development of the UV, mainly for the UV multifunctional coatings, and includes also design of industrial equipment required for the transference of these technologies to industrial scale. So this is very briefly the TECH4WIN. So thanks for your attention, and here you have the web address, so you can connect us or contact us if you have any kind of question or you want further information about us.
Okay, so I'm going to present Impressive project. Impressive means breaking tandem of transparent dye sensitized and perovskite solar cells. So here you can get the website address to visit us. I'm the project coordinator. Impressive objectives are very simple. So we want to take advantage of the light that human eyes cannot see. In other words, we want to make profit of the UV part and the near infrared part of the light to make photovoltaic devices which would be completely transparent to human eyes. So that's the general background idea of Impressive. Now, how to do it? We considered with our colleagues in the consortium that the two main technologies that would be appropriate for that will be the perovskite solar cell for the part of the UV. So why the perovskite solar cell? It's because first perovskite or lead-halide perovskites can have very tunable composition, therefore very tunable band gap absorber. Secondly, we also consider the perovskite solar cell as one interesting technology for this application because it has a very high absorption coefficient and also very low internal energy losses, which will provide close photovoltaic values than the band gap. Within Impressive and related to the development of the UV perovskite solar cells, so we intend to develop, of course, the correct absorber with an absorption threshold below 450 nanometers. We also intend to develop all the components around transparent to the visible eye, so meaning development of transparent all transporting materials and development of the transparent back contacts. In terms of specific objectives here, we intend to develop separately a device which would have 75% average visible transmittance and 6% power conversion efficiency. So this is our specific objectives for the UV perovskite source. In parallel, we are also running with a technology to absorb and convert efficiently the near-infrared part of the solar spectrum. And for that objective, we consider dye-sensitized solar cell because it's a molecular device. So the only way to make selective near-infrared absorber, you need to go for molecular devices, which means either organic PV, LCE, or dye-sensitized solar cell. Within Impressive, we intend, of course, to develop the near-infrared dyes for which the absorbance will be above 700 nanometers, and also to develop all the components around transparent to light, which is the redox mediator and the back contact. Here we also have very important and very challenging specific objectives in terms of aesthetic and in terms of performances, which is 75% AVT and 8% power conversion efficiency. So this is a running parallel work for the conversion of the UV and the conversion of the near-infrared, and we are now at the stage of combining the two optimized technology into a full tandem. So I don't know what happened. Okay, into a four terminal tandem module, which has A4 size, which will be either mechanically stacked tandem or integrated, fully integrated tandem devices. It was also very challenging criteria for the success of Impressive, achieving 55% AVT and 14% power conversion efficiency. With respect to the consortium and the work program, the Impressive relies on 5 important academic partners who are EPFL with Michael Gretzel, the CNRS represented by us, Smart Green Scan by Mariska Debold-Scholten, University of Tor Vergata in Roma, Professor Aldo Di Carlo, and the University of Torino with Professor Claudia Barolo. And we also have on board 3 SMEs, Euroquality, Edge Glass, and G-Light for the industrialization of the technology. The chart is the following. We have a technical core which relies on 5 important work packages. The first or the second work package, but the first technically it's the development of the near-infrared UV perovskite solar cell, development of near-infrared dye solar cell, and those 2 work packages are relying on 2 other work packages which are more transversal. The first one is the design, assembly, characterization of a transparent tandem cell, and on the stability assessment of the separate devices, and also on a characterization toolbox that we do have containing different time-resolved spectroscopy tools. Of course, based on this core, technical core, we have an important work package related to the upscaling of materials, but also upscaling of the devices towards going to the module demonstrator. And afterwards, of course, we have an important work package related to the life cycle assessment and life cycle cost of the technology that we are developing. And we have the work packages related to the project management, dissemination and communication, and also the innovation potential and the business strategy of the transparent PV using UV perovskite technology and near-infrared dye solar cell technology. So later on, I will stop here. Later on, you will have a presentation by Dr. Yuan Liu from EPFL related to the activities of the UV perovskite solar cell, and you will get a presentation related to the near infrared source.